Good evening, everyone. Welcome to Creactive Weekend Talk, episode 210. I am your host, Pratiksha Gowda, and it's pleasure to have you all join us today. At Creactive, our vision is to bring constructive thinking across various domains. We focus on non-textual, non-academic, non-syllabus concepts, encouraging discussions that go beyond conversational learning. As a registered trust, we are committed to fostering intellectual exploration by inviting experts who inspire curiosity and innovation. At Creactive, we organize online weekend talk every Sunday from 6 to 7 p.m. on Zoom platform. We also live stream our talk on Creactive GBD YouTube channel. So feel free to revisit the session or share it with a enthusiastic person. Today we explore an exciting topic, Castle of Glass. Our esteemed speaker, Dr. Abhiram J. Sir. I'd like to call Shravani G to give a small introduction about Dr. Abhiram J. Sir. Over to you, Shravani. Shravani akka. Shravani, you are muted.
Hello. Hello. Am I audible?
Yes, ma'am.
Yes,
Please
ma'am, you are
continue.
audible.
Good evening, everyone. Today I am here to introduce our chief guest, Dr. Abhiram J. Sir. Dr. Abhiram J is an assistant professor in Department of Physics at Sir M. Vishwesvaraya Institute of Technology, Bengaluru, and a recognized research supervisor under Vishwesvaraya Technological University. His research interests span glass science, condensed matter physics, non-linear optics, and functional glasses for optics and bioactive applications. He has published several Scopus indexed papers, contributed to conferences, and is an inventor on an Indian patent related to multi-channel hemolymph collector. He completed his doctoral work in glass science and material science and has over decades of teachings and research experience, including prior services at National College, Jayanagar, Bengaluru. As an active member of professional bodies such as Indian Associate of Physics Teachers and Karnataka Physics Association, he regularly engages with the academic community through workshops, invited talks, and conference roles. In recent years, Dr. Abhiram has also focused on integrating artificial intelligence tools into physics teaching and research workflows, conducting hands-on workshops on researchers, digital toolkits, and delivering talks on AI in physics education. At Sir MVIT, he contributes not only to core physics teaching and mentoring but also to innovation related activities through the institution's Innovational Council. His work reflects a blend of deep disciplinary expertise in material science with a strong commitment to pedagogical innovation and student-centric learning. We welcome you, sir.
Thank you, ma'am. So, thank you for the brief introduction. Can I start the lecture now?
Yes, sir. Yes, sir. You can start, sir.
Okay. Hope the screen is visible to everybody now.
Yes, sir.
Okay. Okay. First, I would like to thank the Creactive Gauribidnur group for inviting me to deliver a lecture on my subject, that is on glass science. So, First, I congratulate the entire team for hosting such a successful lecture series for over 200 numbers. It's not a very small number, but you people are doing it. It's really great. And uh, this marks, even my previous institution when I was in uh, the National College, Jayanagar and Baswangudi, there they used to conduct science forum lectures. So that culture is again being nurtured with the Creactive. I'm really happy with it. And Gauri Bidnoor is also, it is known for Dr. H.N.'s birthplace. So definitely, with this introduction, I would like to dedicate my lecture to my students and faculty members of National College Jayanagar and to my teachers of National College Baswangudi, as well as my colleagues in Sir M. Vishwesvaraya Institute of Technology. So at the onset, this lecture, the entire idea of giving my lecture is going to cover few concepts and historical viewpoints of how we had glass from history to the modern day, and that's what I'm going to cover. And the word glass, it itself, it has come out, it has been derived from a word called as glassen, which was an old German text. And much before that glassen, they used to call that word as gehel. So this gehel was actually a word which was coined for Proto-Indo-European trade in order to have some barter exchange. So that is how the glass came into the existence. And if since we said Indo-European trade, definitely we had vitrium, which was used in Latin, and Mesopotamian, they used to call it as Meko or Ilifako, and in Sanskrit we used to call. There are some Vedic reference that glass has been called as Ranjika, or even it has been mentioned as Kutch. So these are the few references which we had for glass, and that is what colloquially we call the word as glass. This is an English way of calling glass is an extract from old German text, which further roots to Gehel, and it was colloquially used during the Proto-Indo-European trade. So this is a very important material that we are going to discuss in the way how it has evolved over the centuries. So if I have to say, the beauty of glass is being observed since several centuries, but the mystery that we are trying to study with respect to how we have seen this dichroic behavior in glasses and what is the cause of staining in the stained glasses in Gothic architecture. It has been something which is being continuously being explored, and that's how the mastery of nanophotonics, that I can tell you that it was much more available from the Roman era. This, if I have to tell you, here you can see this is on the left side. You see that there is a glass which is actually a wine glass, which is being doped with gold and silver nanoparticles in it. And the beauty of this glass is it used to appear greenish in color. The moment you pour wine, it used to strike the reddish shades. That is because of the presence of colloidal gold nanoparticles, and this phenomenon is nothing but it's the fundamental phenomenon that we observe. It's called as surface plasmon resonance. Similarly, even the stained glasses which we used to find in the Gothic architecture, particularly in cathedral churches, even those glasses, they were doped with colloidal nanoparticles such as gold, silver, or copper. So, the first takeaway message that I would like to tell you is the curiosity on how they have made such materials earlier is the one which we are trying to look for. The science is all about questioning, and how do you question that how these things existed in the history earlier. So much prior to this, if I have to tell you, this is the basic dichroic glass which was used in Roman Empire. But I had been to a site which is called as which is called as Kilamedu. It is near Madurai. So the extracted sites, they had certain glass beads which were synthesized in those days, and there is a very strong connection between the colored glasses that we use today as well as the colored glasses that were found in Roman Empire. So the connection is from a site, or from a site, glass making site, which we call it as Arikemedu. This Arikemedu is a place which was famous for some emporium, glass emporium. So Romans used to call it as Pudoke, and eventually over the decades it started having its name rather than calling it as Pudoke. Even today we used to call city market. Okay, we used to call city market continuously, and over a period of the time it has been addressed as market. Similarly, the pro the Romans used to call a place as Pudoke. Eventually today we call it as Puducherry or Pondicherry. It was basically a glass emporium. So this place, if I have to tell you, they used to make these stained glasses much precisely and effectively. So from Pudoke, it used to go to again Rome, and from Rome we used to get it in the we used to get these things traded in the Mohenjo-daro. So this was something which used to happen in this second century BC or something of that kind. So now, if I have to tell you, further rooting back towards the history of how this glass has been evolved, there is a strong connect with respect to our ancient wisdom. So there is one book which is available. It is called as Amsubodhini. So even in that book, they have mentioned these elements. That is, namely, it is called as Patika, Ranjika, Saikita, Sajikara, Daundika, Shalya Viranji, Kandara, Karbura, Makshchicha, Vajra, Muktika, Danta. So likewise, Naga, Chandrika, Saurika, all these 23 elements, if they are mixed together, they used to form, and the temperature is around 300 kakshas, which leads to formation of a glass that leads to, Sahasra Jyotis. It is trying to give you a multiphotonic effect when the light falls onto such materials. So the one which we are trying to talk today, for example, a glass laser, which came into the existence by Schneitzer in the year 1962, if it is dated, where they have come up with the neodymium doped this particular glass, which was patented by Schneitzer in 1960 or 61. If I have to tell you, this book, which has a translated version in English, was published in the year 1932. So there is a correlation. I am not trying to tell that Schneitzer has used the exact thing. I'm just trying to tell you the idea, the thought process of glass being an active photonic material existed since 4th century BC is what this book claims. And further, if I have to tell you, the global connect was always there, and that is how we have to actually, the moment when we speak about where do you start your research, particularly in nanoscience or nanotechnology, most of the books they cite with the foundations of that particular Lysergus cup, which I had shown you earlier. But if we can collaboratively start exploring things that were present in the Indian knowledge system, and if you start questioning things that were existed in our ancient Indian knowledge, and if you start probing into it, probably you can find a lot of problems to solve. So this is a small introductory message on how glass can be explored further. And further, if I have to say, the journey of glass science that we are trying to see, it has started from the obsidian glass vessels, which were in the 2600 BC, and in the 17th century, Galileo's optical lenses, which gave us a precision optical material, and in the year 1932, glass theory started becoming very much dominant. That is where Zacharian came up with his beautiful oxide glass forming rules. And in 1950, chalcogenide glasses came into the existence. And further in 1960s, Schneitzer, as I told you earlier, Schneitzer came up with his glass laser. And today we are trying to look for the 3D laser writing that can be embedded inside the glass, or we are trying to look for flexible photonic devices, and that is where we are trying to go ahead with respect to the research when we are trying to look in respect to with respect to glass science. So if I have to tell you, one of the strongest structural foundation that was laid, it has to be remembered. We have to. It is. There will be. It is. There is no doubt calling Ernst Abbe as father of the modern glass science and technology, because he had started coming up with lot of problems solving optical dispersion and spherical aberration, and it was not possible individually by a physicist. It was supported by a chemist. He was none other than Otto Scott. Otto Scott had a beautiful history. His DNA roots to making these glasses. So he had an interest on synthesis of these glasses, and Scott and Abbe together, when they were trying to solve several problems that were during the World War II time, and we had an investor for them who can actually scale up the glass science towards the optics, and that's where Carl Zeiss came into the picture. And Carl Zeiss, Scott, and Abe together, they started building wonderful glass science and glass instruments, optical instruments. In fact, that revolution has led to the modern renaissance of glass science. So, if I have to say, that is something which happened in the global level, and this is an interesting story which we have to remember, particularly a student of glass science, that we had one of the most wonderful person, that is Ishwar Das Varshney. He had gone to MIT in 1904 to study the amorphous structure, and later he started learning the art of glass science. And in 1910, when he returned back, with the help of Tilak, he started something called as Paisa Glass Works. So it was the first glass industry that was established in India, and further, they started growing the glass technology, glass science technology over here by 1930, and their sons also, they contributed immensely for development of glass science. And Ishwar Das Varshney was the first, he's the founder, president, and chairman of Ceramic Society, Indian Ceramic Society. And he was also one of the most key person in establishing Center for Glass Science and Research in Kolkata. So, we don't try to remember such wonderful people who had been here to establish glass science. So I would rather like to call him as father of Indian. He has a title which we call it as father of Indian glass industry. I could rather call him as he is the pioneer who has established glass technology in India. So today, if I am working in the field of glass science, I am thankful to all these people who have immensely contributed in my field. So now, before defining glass, so what actually we need to look for. So what happens when you look through a window? You see there is a glass which is placed over there, and you are able to see the light coming outside from outside to here. So it just looks very ordinary, but it is not an ordinary phenomenon. It is the physics behind it is very much impressive. Normally what happens is the ultraviolet radiations gets strongly cut off with the glass, and what you get is the visible radiation. So glass has lot of significance in abstaining or in absorbing the ultraviolet radiations, which are harmful to our skin. So now this material, it has different structure and different behavior. If it is transparent, it can be used as window. If I'm able to slightly have its curvature, it behaves as a lens where I can focus the light. And if I try to draw it as a draw it as a wire, then it becomes an optical fiber, which is how we are connected today. Okay, and further is when it is sensitive to the intensity of light, it leads to formation of new class of material which we call it as smart glasses. So this is completely, glass is something where you can start playing around. If you are trying to fool around the atoms which are present over there, definitely you can start having the control over them. So what is glass? So every day we try to say it's a transparent solid, and which is used as windows, bottles, screens, and lenses. That is where we try to find. And if I have to talk with respect to the way how I visualize it, it is nothing but, it is just a frozen atoms which are in the, it is just an atom which has been freezed suddenly, when it is brought to the rigid condition. So a glass is a non-crystalline solid that surpasses the glass transition temperature, and it has been cooled to a rigid condition. This is what we try to say. So it is not just simply, you cannot say that it is solid material and which is transparent. So it is how do we define them? So here ASTM defines that glass is an inorganic product of fusion which has cooled to a rigid condition without crystallizing. And in 2015, glass is a non-crystalline solid which exhibits glass transformation range in volume or enthalpy temperature relationship. So you have two different temperatures. One speaks about how it is being obtained, while the other says about its particular property, which is called as the exhibition of a glass transition temperature. So my co-guide had defined a new definition for glass by combining all these phenomena together. Glass is an amorphous solid which exhibits glass transition temperature by arresting the kinetics below the supercooled liquid region when surpassed crystallization, when it bypasses the crystallization. So how do we understand this definition? So if you just observe this time temperature transformation curve, you can see that there is a C curve, and you can see that there is a line which is being drawn. So below the nose point of that C curve, whatever you try to do, the material is undergoing the supercooling. But at that particular nose point, the material undergoes the crystallization. So to further visualize this, so here I can tell you, if it is a perfect crystal, it has a unique melting point. So the moment when you heat, it is solid, and at some point of time, it becomes completely liquid. But with respect to glass, what happens is it undergoes an expansion. So when it is undergoing an expansion, it is being knocked, you have knocked a door which is called a supercooled liquid region. After surpassing, sorry, it is called as glass transition region. After surpassing that region, it undergoes the liquidus phase. So now, here when I have to tell you, so crystal, they have a stable equilibrium. But glass, it has a metastable equilibrium, which means that it is being arrested. When the moment when you start quenching the material, immediately from 1200 degrees Celsius, say for example, you can just imagine, okay? It's just an imagination for you people. So if I try to give you a cup of hot water to sip, okay? If it is at 100 degrees Celsius, you will not try to have the water immediately. You will try to take some 10 minutes time where it has to cool down to approximately around 40 or less than 45, less than 30 degrees Celsius, where you can, you can sip the water and drink. Whereas, if I tried here, I am trying to play around a temperature which is 10 times of it. I would have I would have melted the material at around 1050 degrees Celsius, and within 2 minutes I am able to touch. So, which means that all these atomic moments which were free, when you see that in the liquid phase, the atomic moment, the symmetry is free. The moment you quench them, before they try to form the symmetrical structure, you have actually holded them. You have told them to be in the freest state. It's like, we used to play earlier. I don't know how many of you have played this game. Suddenly, we used to say statue. Okay. So, this glass formation is like that. You say statue to it. The moment when you quench, all these atomic moments are being frozen. And if I slightly reheat them at that temperature, okay, this free energy and this temperature can be correlated. If I slightly reheat them at that particular temperature, again it undergoes crystallization. That is where it tries to form a quasi-crystalline material. So now this playing around this metastable equilibrium is something which is important. So now, how do we design this glass? So we need to know what are the ingredients. Okay. So the basic building ingredient is called as network formers, and the framework that you try to build is called as network modifier. And how do you switch between a modifier and framework? And that is where the intermediate plays a very crucial role. So if you are trying to change the composition, then there will be change in structure, and eventually there will be some change in the property. So now let me take you to the kitchen. So here, what kind of elements belong to the class of network modifier, and what kind of elements belong to the class of network intermediate, and which one belong to the network former? The low coordination uh, number, if it has the low coordination number, say per se boron, silicon, okay, they have a very low coordination number between 3 to 4, they fall into the category of network formers. High coordination number like alkali metals or alkaline earth metals, they fall into the category of network modifiers. Some, some elements like lead, zinc, they have a coordination number ranging between 4 to 6. They fall into the category of intermediate. So at the lower coordination number, they become like former, whereas at the higher coordination number, they take the role of modifier. So if I have to tell you, this is the periodic table. So in the periodic table, you can see where is the lithium, magnesium, calcium, strontium, they all belong to the modifier group. Whereas if you see here, boron, silicon, phosphorus, germanium, arsenic, okay, tellurium, all these elements, they fall into the category of glass formers. So in between them, wherever you try to see zirconium, okay, or bismuth, they all try to play a role, crucial role, which we call it as an intermediate role. So now, what these modifiers can do inside the glass network. See, it is like, if I have to tell you, you have rava as an ingredient over here, and you know addition of salt, a very little quantity of salt can change the taste of the entire upma that you are trying to make. So similarly, the role of alkali oxides are or alkali modifiers are like that. Okay, they are called as classic modifiers, where they know whether to build the network or break the network. Okay, that depends on the composition that they are trying to deal with. And if you're looking at the heavy metal oxides, they play a very dual role where they are having a role of 50-50 chances where they can become a modifier as well as a former. So, for example, if I have to come up with high refractive index glasses, or if I have to come up with high radiation shielding glasses, I would definitely go with the lead oxide or a bismuth oxide for this particular matter, or even barium oxide, which also falls into the alkaline earth category, but still it is an heavy metal. So therefore, they also play a very crucial role in this particular phenomenon of shielding glasses. But if you're looking at fluorides particularly, these fluorides, they are charge compensators. So what they do is they try to break the oxides and they try to form a separate bond with fluorine over there. So because of this, a defect center is being created within the network. So these defect centers, they play a very crucial role in tailoring the optical properties of these glasses. So now, if I have to take you back to 3500 BC, the traditional way of formation of glass was by blowing the sand, and that's how they used to make the glass. But today, in modern day, how do we prepare glass is, particularly in lab scale, if I have to tell you, we try to weigh the sample, and then we try to have a batch matrix, and then we try to weigh the sample, and then we try to pulverize it. We ensure that the amorphosity is being maintained, and we transfer it into a crucible, and we place it inside the muffle furnace. Once it is being placed inside the muffle furnace, we don't directly, it is not advisable or recommended to quench directly at the melting temperature. What we try to do is we try to initially, we try to set it at 150 degrees Celsius. So we are trying to expel the hydrates. So for 150 degrees Celsius, we try to hold it for around 20 minutes or 30 minutes. And later we try to switch it to 438 to around 415 to 420 or 430, 440 up to that temperature. Between 410 to 450 degrees Celsius, if I'm able to set, I would be expelling chlorides, halides particularly. And if I try to set it at 600, that is around, need not be precisely 600. It could be from 600 to 650, depending on the batch that you prepare. So if you are trying to set it at that temperature, you are trying to expel the carbonates that are being used from your precursor. And finally, you can quench the sample at 1050 degrees Celsius or 1100 degrees Celsius or 1000 degrees Celsius or 800 degrees Celsius. Depending on your batch, you can start playing around the temperature. And once the liquid is being formed, you try to take it out of it, you immediately pour it, and this rapidly it solidifies. And once the glass is being solidified, again you try to place it inside the furnace. So that's what you try to do. So you can see how these glass has been made. This is another technique which we call it as microwave oven technique. It's just a video to visualize for you. Okay. So this is a very simple low cost synthesis that I am trying to propose here. So this I was fortunate to do a seed grant project in my previous institution, that was Indian Academy Degree College, where we started coming up with, we came up with a very simple microwave technique. was my colleague, Dr. Vivek, my the co-principal investigator of this project. So it was just a small test that we are trying to do. And this is how we try to do. So we can change the way of synthesis right from conventional melt quench technique to microwave technique. We have several synthesis, but there is one challenge with respect to this. One of the major challenges, if you're trying to go with the microwave technique, which is the modern technique, if I had to say with respect to melt quench technique, I had lot of window open to synthesis glasses. But with microwave, I have to be very cautious. I have to choose a proper host matrix which are susceptible to microwave. Then second one is the microwave wattage has to be nearly greater than 800 watt. Lesser than that, again, the window of having the obtaining the glass is very less. The probability of formation of glasses are also very less. And the choice of crucibles that we need to use for these microwave should also be susceptible. So I have to go with a silica crucible or alumina crucible, which is going to be very much expensive. Say, for example, in the melt quench technique, if I had to use, I can just pay nearly 70 rupees per crucible and get my sample done. Whereas here I have to spend nearly 400 rupees per crucible, which is very much expensive. And further, the exposure time and managing the thermal stresses, it depends based on the microwave exposure and how it is susceptible, where it is being placed. All these things plays a very important role. And the most important challenge is the moment there you can see there was a reddish color that was being found in the crucible. Here, crucible doesn't become red, but only the glass has undergone its molten phase. So the moment you remove it outside the microwave environment, it quickly solidifies. So the yield that you need to get from microwave is also less, but there is an advantage, because since since microwaves strongly absorb any water content at 2.1 megahertz. So therefore, uh, the entire water content that are present over there, it gets absorbed completely. So that is where you find this challenging. Now, how do you make the glass look colorful? So it is like again going back to our Upma experiment. How do you make Upma colorful? Or how do you make kesari colorful? You add a coloring agent. The coloring agent is not used in larger quantity. It is used in a very smaller quantity. Say for a per se, if I have to use turmeric, I don't use turmeric in the larger quantity. I just use it in a very nominal, very smaller quantity, which is much more smaller than the salt quantity. Similarly, even here, we try to use the dopants such as vanadium, chromium. See, all these elements, that is 3D transition elements or even the 4F transition elements that are present here, and even the noble metal nanoparticles that are present here, they can be used as the dopants. So if I use europium, I can get some reddish color. If I use cerium, I can get bluish color glass. Then I can get with silver, I can get bluish color glass. So that's how you try to come up with glasses. So now straightly let us get into the optics and photonic devices. So the major challenge that we try to find with respect to Nd:YAG crystal, okay. So we have two different kinds of materials. You can see this is Nd:YAG crystal and this is ND glass laser. So what is the fundamental difference that you try to see between them is the one is the structure, The other most important thing is this Nd:YAG crystal is typically used for continuous laser, for the design of continuous laser, whereas ND glass laser is used for pulsed beam laser. So now, with respect to the colors, if I have to say, you can see this particular europium, cerium, samarium, dysprosium, manganese, silver, they are all showing this. They are all showing this particular shades in this blackish region because it is with respect to the exposure of UV light. Whereas these colors that are being obtained for the other transition metal elements, it is because of the visible region. Okay, so having said and done, we shall slowly get into the next important part, that is, why do we need to add very smaller quantity? What does it do? It tries to change the size as well as shape of the particle, and that's how the glass environment gets into different kind of structure. Now, what is the fundamental difference between the crystalline solid as well as an amorphous solid? So in crystalline solid, you see that long range ordering, whereas in amorphous solid, you try to see there is no long range ordering in it. And how do you get to know about it? One is by XRD, where you make the structural characterization. The next, but again, the structure that you try to see, since it's an amorphous network, since there is no long range order in it, there is no point in getting any conformal signals from it. Then FTIR speaks about how the bond is being found between the BO4 region or BO3 region or SI. It just gives you the molecular bond structure. It doesn't clearly tell you how exactly is the structure of the glass that is being present inside. So you are not able to get complete information from one single characterization. So you need to club all these characterization and then you have to interpret what exactly happens. So when you look at UV with spectrophotometer, you get the optical response, you get the band gap property, and you can also calculate the apparent size of particle through the Mie scattering technique. And through SEM and TEM, you can speak about the shape and size of the particle. And through Z-scan, you can look at its nonlinear behavior. So that's how you try to check them. So when you look at XRD, what normally happens is you see a very broad hump that is present here, and there is a small kink that you try to see at around 38.16 degree. So here, this is that this normally it doesn't appear if in a pure glass, but if it is being doped with some nanoparticles, you can confirm its presence by this. So this is where one of my work where I have shown the existence of gold and silver coagulated nanoparticles in the lithium, strontium, zinc borate glasses. Okay. So now, what exactly happens in the glass with respect to modifier? This modifier, it goes on breaking the bond. And once it breaks the bond, the structure of the glass will loosen. And eventually the density of the material drops and thermal expansion rises. This is what we expect, and that is what we have observed in the silicate glass matrix. But when you look at the borates, there was something that started, there was something which happened in a different manner. Up to certain concentration, it followed the behavior that you try to see what happened with respect to silicates. But beyond that concentration, what happens is the structure started tightening, the density has increased, and the thermal expansion started falling down. So this led to formation of BO4, strong BO4 region, and again after 33%, it again loosens its structure, density falls, and that is where it leads to an anomalous behavior, which we call it as boron oxide anomaly. So normally what happens here is it is undergoing that squeezing effect, and because of the squeezing effect, you try to see that, okay, because of the structural tightening, what you try to see is they try to undergo this anomaly. So once the anomaly appears, it leads to formation of non-bridging oxygens. So normally what this anomaly does is, say for example, borate, if I have to say, both these are the two premier glass formers, that is borate as well as germanates. They exhibit anomalous behavior. So normally with respect to boron, what you see is they are three coordinated planar structures, whereas in germanium it is four coordinated tetrahedral structures. So what happens here is, initially this trigonal borate groups, they bridge together to form the tetrahedral borate structures. Whereas when you're looking at germanate, what happens is it shifts from the coordination from tetrahedral to octahedral, where it leads to formation of much compact networking beyond 33 mole percent. Okay, what you see is the network which were converting it into the trigonal into the tetrahedral boron, they suddenly they depolymerize to form once again the trigonal borate groups. That is where it starts forming an anomalous behavior which leads to generation of non-bridging oxygens inside the network. Similarly, you try to see the same kind of behavior, but here what you see is within 15 to 20 mole percentage of alkali dopant inside the germanate matrix. From the octahedral germinate network, it starts reverting back to formation of tetrahedral borate groups. So this is how the non-bridging oxygens are being formed in these glasses. So why do I need this? There is a flaw in this feature. So now what happens is, usually glass, it wants to crystallize. See, what are the things I told you? Initially, it want to crystallize. It want to, get itself arranged. It want to exhibit long range ordering, but you have arrested it thermodynamically. So there is a structural disorder in the network, and the structural disorder is on one side. And when you are trying to say that if you are trying to increase the modifier content, with respect to borates or with respect to germanates, it is exhibiting one more anomalous behavior. So this is completely a chaos that is being created inside this amorphous network, and this chaos is something which is useful for us. It will enable us to come up with new optical properties. So now, before getting into the optical property, one of the major thing that I would like to tell you is the glasses are also found to be effective, particularly in bioactive region. So how these bridging oxygens and non-bridging oxygens help in bioactivity is what I'm going to tell here. So if the bridging oxygen is 100%, which means the high network connectivity, they are highly stable. So when they are highly stable and if the network connectivity is very high, they will not try to dissolve or interact with any bodily fluids that we are trying to use. So whereas on the contrary, if you are going with higher NBO content, it starts interacting with the bodily fluid, and because of that, the bonds undergo ion exchange, and thereby it leads to formation of new tissue layers, or it also leads to formation of hydroxyapatite layer for bone regeneration. So these are the two different things that you need to observe. So if you increase the modifier content, eventually you are increasing more NBOs. If you are increasing more NBOs, then the connectivity between the network is lowered. If the connectivity between the networking of the glass is lowered, that means the bioactivity is again increased. And if the bioactivity is increased, then possibility of degradation is also much more quicker. So these are the things that we need to remember. And the moment when you look into the melt quench technique, this can be synthesized in two different phases. One is the basic melt quench technique, and once you have quenched it, here you don't try to actually prepare it in the glass as a glass which is highly transparent. You can also come up with BG powders, biogas powders. Okay. So the moment you form the powders, you have to mill them. And again, what you can do is you can mold cast them and you can check for its dental applications. And you can also check those biogas powders for any, whether it can be used as any therapeutic agents or some or of any of that kind. So if I have to tell you, these three oxide glass primary network formers, that is silicate, borate, and phosphates. If I have to tell you, the structural geometry of this is going to be 3D tetrahedral in case of silica. Here it is mixed planar or tetrahedral in case of borate, whereas in phosphate it is flexible chain structure. And if I have to talk about the degradation rate, in borates, it is highly degradable, whereas in silicate, it is very slow, whereas in phosphate, it is tunable. So the mechanism of action of formation of hydroxyapatite layer is common for all these three things. But if I have to, create a rapid angiogenic result, ion release, that is to create the blood vessels, then I will go with a borate as well as a phosphate network that is called as borophosphate classes. And if I have to, completely mimic the nature of bone, then I would definitely go with the phosphate glass network. So, if I have to tell you, I can easily use, I can easily put all these things into one particular way where the silicate can be used for dentistry or hard tissue engineering or orthopedic, and phosphate, this is very important that we would have observed it even today. Any tablet that you try to purchase, you can see that every drug it has I dot P. I dot P stands for inorganic phosphate. So easily they fall into the drug delivery category as well as the specialized soft tissue. And if I go with borates, I can go with bioactive coatings or soft tissue engineering. So this is how you try to play around with bioactive glasses. Now, the most important part is how do you control the light? So there are four, this is nothing but we have come across these things. The first thing is passive scattering, the colloidal nanophotonics and dichroic staining that we have seen it since the Roman era. That is where the history was. And refractive control, the industrial design that was laid by Abbe and even Ishwardas Varshney. Okay, they came up with this precision optical instrumentation. This was something which happened in industrial scale, and currently what we see in the modern day technology is this dopant driven lasers or flexible gain media that you are trying to see is something which is happening in modern day. But tomorrow what we see is PICs and the trapped ion evaporation substrates, or even TVGs, which we call it as through vial glasses. So they are all going to be the next generation that we are trying to see in future. So now, if I have to talk about the photonic part of it, what I can say here is not all glasses, sorry, so not all glasses are having the same kind of feature. But what you try to see here is when I deal with something silicates or phosphate, they play a very important role in high rare earth solubility as well as they're highly visible. They play a very good optical properties in visible or NIR region. When I deal with fluorides, I can tune it around in the mid infrared region because of its low phonon energy. They enable themselves to be visible in the infrared region, and they are transparent in the visible region, in the infrared region. So if I have to look for chalcogenides, they have high refractive index. Because of their high refractive index, they exhibit this non-linear optical properties. So now where exactly I am trying to look for, because today's modern day technology, it requires mid-IR region, so solid state laser, which is extremely important. So what I try to say is if you're trying to play around, you just look at the transmission window region of silicate, it is only visible to NIR. Whereas if you're looking at chalcogenides, it is between deep mid IR. But if you're trying to look at this fluorides or oxyfluoride network, it is ranging between UV to mid infrared region, which is very much important because you are trying to play around the entire water window, with the so-called water window, where you can find a lot of tissues, cell. So thereby they enable they make themselves enabled for biomedical diagnostics. So that is where we try to look, or we try to check for the fluorides or oxyfluoride networks as one of the major glass host matrix that we are trying to design for. So now I had already briefed you how the process has to be. It cannot be directly, the quenched technique. It has to be step process. But again, even post melting temperature, it has to be annealed for certain temperature. And annealing has to happen at 400 to 450 degrees Celsius. It has to be held for 2 hours or 3 hours. And it depends on how you want to prevent the non-bridging oxygen disorder networks. Based on that, you try to tune it. You can anneal the sample up to 6 hours or 8 hours. So when you are trying to play with it, what you try to see is you are enabling this glass to draw the waveguides inside the material. So that's how, because this is one of the most important challenge that we have. We have something called as beta barium borate crystal, which is available in the market for second harmonic generation. But the challenge is this beta barium crystal is highly hygroscopic in nature. So barium borate as a glass, it is highly stable in the region. It is not hygroscopic. But the problem is, since it is a glass, it cannot exhibit second harmonic generation. So if I have to trigger that second harmonic generation, I have to break this isotropic nature of the glass. So how do I break them? That is again by controlled thermal agitation, that is through thermal annealing. I will slightly break, and I had already told you it has a metastable equilibrium. From metastable equilibrium, I'll try to push towards the stable equilibrium. If I'm able to slightly tune that, I can definitely design a glass. I can definitely draw a waveguide of beta barium borate inside the glass matrix, which is completely encapsulated. That beta barium borate, which is hygroscopic, but it has been encapsulated with a barium borate environment, which is completely stable, and thereby the hygroscopic challenges are being reduced. So this is one of the major challenge that is open to all of us. As students of glass science, we can work on this line. And what normally now, after telling this, when it comes to the application part, it normally it acts, it just says whether can we control the light, or can glass control the light. The thing is, we are just going to look how it is into the controlling of light mechanism. So normally, from the consumer point of view, if I go and ask, they can say, every small little kid, they can say that looking at smartphone, they say that, yeah, I'm able to see there are some, glasses found in this particular gadget. And some might, they can say optical fiber, where we can find some glasses. And some might also, check and tell, I have found some literatures, or I have found some interesting pulsed beam lasers which contain glass as one of the gain medium. But this is from the consumer point of view, or this is from the engineering perspective. But as a material science student, what I try to see is it's completely the structure property relationship inside the glass. So now I need to, ensure that the photon has to undergo this tracking. And particularly, this is not a passive window. So I have to make sure that it listens to me. So I should know where to bend, or where to amplify, or where to make sure that this particular device remembers the pathway of the light. So that is where we try to manipulate this glass network. So we have two different case studies. One is using it for luminescence, and other one is using it for the nonlinear optical properties. So now coming to the basic material, here you have Nd:YAG glass crystal. Here you have Nd:YAG crystal as well as Nd glass laser. So in the Nd:YAG crystal, what you see is the lattice. The structure is it has a crystalline structure, long range ordering. Whereas here it is not a long range ordering network. So random network, which we call it as an amorphous medium, and thermally they are highly conductive. Whereas here, you know, they can try to ensure that the material doesn't undergo any significant thermal agitation. And again, what you try to see here is the application is for continuous wave laser, whereas here you try to see it for pulsed beam laser. So one of the first one of the first research-based laser of ND glass laser, which was used for nuclear confinement fusion reaction, was called as Shiva laser. It was used in Lawrence Livermore Laboratory. They were trying to come up with, by using these lasers, they were trying to build a small kind of tiny stars inside the laboratory conditions. Then they came up with several lasers. So that's how, the laser plays a very important role even in high energy physics that we are trying to deal in the research part. So if I have to come up with the role of plasmonics in these uh, rare earth based glasses, what I try to see is there is something called as resonance energy transfer that occurs between the localized surface plasmon resonance with respect to the emission wavelength of that particular material. If these two things are being undergoing the energy transfer, what happens is they act like antenna. This surface, nanoparticles, gold or silver colloidal nanoparticles, they play a very important role. Like they act as plasmonic antennas. So the moment when the emission occurs at around 647 nanometer, it acts like a booster. So it pushes the signal light emission that you are trying to see with respect to europium emission. So similarly, what we try to see is we try to see a nonlinear effect. So this is an schematic sketch that you try to see here towards the left corner. It is a schematic sketch of Z-scan instruments. So what you see here is from the laser, it falls into the mirrors, and then there is a stage over here. So here you place the sample at a particular point, that is at the focal point, which we call it a Z point. Okay. If the glass intensity gets magnified, we call it as an optical switch. If the glass intensity drastically falls down, then we call it as an optical limiter. So this is a very important mechanism that we try to see. So this is where it is trying to change the behavior of light. Here it is trying to actually, manipulate the light mechanism based on the focal point that you're trying to see. So that is why these materials, they fall into the category of smart glasses. Now, if I have to talk about the next generation semiconductors we are trying to look for, one of the major thing that we try to see is called as glass semiconductor. So in the, that we are undergoing this Moore's law limitation, it clearly says because of, bringing the narrowing down the scaling down the transistors, what you're trying to see is the 2 nanometer chip. You are trying to bring the two silicon atoms closer by. When you're trying to bring them closer by, definitely it undergoes lot of thermal agitation, and because of that, there is a disruption in the entire chipset. So that's why Intel has come up with chiplets, okay, where glass is used as an interposer. And what makes them advantageous is because of the dimensional stability. Why? Because you are trying to replace a dimension which is of 3D dimension or 2.5D dimension. And second most advantageous part that you try to see is they have higher interconnect density and much better thermal and power efficiency in this particular material. So they are coming up with this. So IonQ chip, they have come up with something called as class, which we call it as quantum glass based photonic integrated circuits. So even this is in the research stage. Probably in the year 2028 or 2032, they will be coming up into the market. So these are all used for multi-core quantum computers. So that is where glass is finding its place, particularly in the photonic, it plays a very important role, particularly in photonic integrated circuits. And what exactly is required today in this hour is what we are trying to say. So now we have two different processing. So conventionally, now we are trying to deal with electronic AI processing. So, because of this Moore's law limitation, what you try to see is they undergo a lot of physical, they will undergo a lot of thermal loss. Whereas when you are trying to use a photon, what happens here is, you know, the advantageous part is they experience zero resistance in vacuum, and thereby, you cannot see any thermal footprint inside this particular matrix. So now it this is on one side. The other side is very much alarming. Okay. That is something which we call it as we have redefined the carbon footprint. So one is the operational carbon footprint, which is electricity driven carbon footprint. The second one is embedded carbon footprint, which we are not aware of. This is these hidden emissions which you try to see, it completely occurs in the data centers. So normally what we try to see is the embedded carbon footprint is, it is going to exceed up to 80% or 90% emissions as you go ahead in next few years. And the amount of AI that we are trying to use in the contemporary world with respect to the embedded carbon footprint, it is going to be much more higher. And that is where, the photonic computing is very much required. And that is where the research has to progress extensively in this particular field. So far, what we have done is we were successful in coming up with tunability of SPR. We were able to establish the nonlinear response, but still this is the phase 3 and phase 4 part, that is optical logic gates as well as the photonic computing part. It requires more emphasis. So probably the students whomsoever they are studying sciences, they can start working on it from day one, and they can start learning what exactly is required to address such problems. So now this is this is just an extract of Xenado's photonic quantum computing chip. So here you can see that when the laser beam falls into it, here you have micro ring resonators. So through resonators, it falls into the Mach-Zehnder interferometer. So that is where you know through the entire network that you try to see, it requires glass, which plays a very important role of optical interconnect here. So that is, again, it is going to make the material to be, advantageous. So when it falls through this ring resonator and when it enters into the Mach-Zehnder interferometer, they undergo squeezing, which we call it a squeezed state, and these squeezed state forms the entangled photon which are being formed, And these entangled photons are being found by a phenomenon, as I told you earlier. It has to be through spontaneous parametric down conversion. So there we make use of the photonic crystals. And if I have to interconnect these layers everywhere, the glass plays a very important role. That is where the glass interposer technology plays a very important role. So now, if you are trying to look into it, the major photonic highway that I am trying to say, it requires high bridging oxygen glass in the silicon network. And if I have to, that is in the cladding part. But if I have to go with the manipulation part, if I have to manipulate the light, there I need to use high non-bridging oxygens. So that is where you have to know how to switch between a bridging oxygen network to the non-bridging oxygen network. So that is where we try to jump with the co-doping of rare earth elements, and we try to enhance the lasing action inside the particular device that we are trying to deal with. So if I have to tell you the assembly for this, so if I am trying to use the interconnects, I need a high bridging oxygen. But if I have to manipulate the light, then I need high non-bridging oxygen network. So you should know what kind of material that you're trying to use and how exactly you're trying to play around with this. So that is where we need to look for it. And this is just to alarm everybody. See, the cumulative carbon emission that you are trying to see with respect to the silicon chipsets that you are trying to see, the one which is conventional nowadays, it is going to raise over the period of next decade. You can see it is going to be so high. But if it is being switched to a photonic accelerator, okay, a linear transmission photonic accelerator, what you see is you try to see there is no much carbon footprint that you try to see. Because why do you see this? Because you try to see because of the embodied carbon footprint. But the operational carbon footprint is not going to be so high. It is all because of the embodied carbon footprint. So one small assignment that you can check. You can ask Gemini or Chat GPT or Claude. Directly you ask them. We have become so lazy even to draft a letter. We used to write the prompt to Chat GPT and ask them to draft a letter for us. So you just ask the same Chat GPT to just write one letter. What is the amount of carbon that is being emitted in the data centers, as well as what is the amount of water that is being consumed to cool the data centers? If you just look into it, you will get to know, to just write a letter to you, it bribes nearly 535 ml of water. In this case, the way how we are using AI exponentially, I can tell you in future, the war for water is not going to be between the two states. Rather, it is going to be between the human and AI. So use the prompt effectively is what I would like to tell you. And I would just, based on my things, what I would like to tell you is glass science is alive, and you can try to do whatever kind of research. It has expanded so much. Okay. I have just told you about the two applications, very two small applications, but if you're looking into the solar, again, glass is available. If you're looking at the smart windows, again, glass plays a very important role. So you have lot of scope to explore. And tiny particles like gold, silver, copper, nanoparticles can change its behavior abruptly. So to study this light matter interaction itself is something which is much more interesting. And science is not, it is not like You cannot always define science as a journey. You cannot say that science is going to be like this. Yeah, I am precise. After this is what is going to happen. Every time, the unexpected results are the one which are going to lead to birth of new branch of physics. You know, if there wasn't any question with respect to the photo, if there wasn't any question with respect to black body radiation, we wouldn't have had quantum mechanics today. And that's where, it is always an unexpected result that leads to new, it tries to give birth to new age sciences. So I would like to thank all my institutions that were supportive enough for molding me and making me stronger uh, and better to learn this subject. And I am thankful to my family members. Without their support, I'm not anywhere. I mean, I wouldn't be able to deliver this talk. And I am thankful to my guide, Dr. Raj Shekhara KM, my co-guide, Rajaram Krishna, and Professor Jakrapong, who have helped me to gain more insights in glass science, particularly during my PhD tenure. I'm thankful to Professor Soma Venugopal Rao for his beautiful insights on nonlinear optics. Dr. Jagannath, he is currently working in CGCRI Kolkata. He has been the biggest pillar or strength or support to me for understanding for understanding, writing, and reviewing my paper during my doctoral tenure, particularly with respect to nonlinear optics. I am indebted to Dr. Ranjan R.V. Anvekar during my first interactions on glass science. I am thankful to my doctoral committee members, Professor Giraya, as well as Professor Ayachit, who have given me valuable insights and tuned me up to learn much more deeper insights on glass, particularly the structural properties of glasses. And I'm also thankful to my collaborators, Professor Sudhakar Reddy as well as Professor Shivshankar Reddy, who had given me wonderful insights, particularly when I was working on microwave driven synthesis on glasses. And I'm thankful to all my research colleagues, Dr. Vinayak Pattar, Dr. A.R. Venugopal, Dr. Sanjay. Without their support, we had a lot of fun spending in labs up to night 1 a.m. or 2 a.m. So that was the joy we had together, and that is the time where we started understanding much more insights on our particular materials that we synthesized. And I am thankful to all my bosses, right from Professor Sheshadri, Raghutam sir, KT Vasudevan sir, P. Nagaraju sir, Shyam Sundar sir, Dwaraknath sir, my principal at Sir MVIT, Professor Rakesh, Professor Tipeswamy, and Vice Principal Professor Bharti Rao, and my head of the department, Dr. Hariharan, who have been constantly supporting me to participate in the knowledge exchange program. And I am also thankful to STIC Kolkata. STIC, that is sophisticated, this one DHT based, this one characterization facility at Cochin. So they have helped me in characterization of TEM analysis, and I'm thankful to all my friends, Chetan, Pramod, Dr. Pramod, Dr. Rajgopal, Dr. Sumanta, Dr. Siddhu, Dr. Tejas, Dr. Shivraj Maidur, Dr. Pavan, Dr. Malvika, Dr. Manjunath, and Dr. Vivek, Dr. Ganesh, Arvind, Jagannath, Kaushik, and without them, I am nothing. That is what I would like to tell you. So the quest continues. Science does not make the world less mysterious. It teaches us to ask better questions about the mystery. So that's what I would like to tell you. Thank you very much for your patience hearing. Any more questions?
Hello. Sir.
Yes.
Good evening, sir.
Good
Myself
evening. Good
Ganesh.
evening.
Yes,
Okay.
sir.
Am I
Myself
audible,
Ganesh.
sir?
Yes, sir, I'm audible.
Okay. Okay.
Myself Ganesh. So I am a creative associate and
Okay.
currently I am a research scholar at NIT Surathkal.
Okay, sir.
So I met you in KPA conference in Vijay College. I
Oh,
hope
yes,
last
sir.
year. Yeah, last year I think.
Okay.
So I am also working here in glasses. So it
Good,
was a
sir.
nice talk
Thank you.
and I gained some knowledge. Not some knowledge, I got more knowledge in this talk.
Mm.
So I have some questions, sir.
Yes, sir, please.
Uh, so suppose my composition is X, some
Mm.
borate silicate.
Mm.
So is there any like proper methods to determine the melting point of that composition?
Okay. How do you determine the melting point?
Yeah.
You normally what we do is we try to look at, I can tell you a crude method. One is, normally what others do is they try to look at the reference. So for example, if I don't have any reference paper, I'm trying to come up with my own new glasses. Okay.
Yes.
The crude method, what I try to use is, it's cooking, no? Chemistry,
Yes.
it's all chemistry about. So what I try to do is I try to check for the melting point of my former, melting point of my modifier,
Okay.
and much importantly, what I see is I see the Gibbs free energy.
Okay.
If the Gibbs free energy is negative,
Okay.
then I can play around the melting point with respect to former.
Okay.
If the Gibbs free energy is positive,
Ah.
then I have to play around the melting point of the modifier, the one which is highest.
Okay. Yeah.
That's the method that I use. Okay, that's the secret.
Okay, sir. Thank you.
Okay.
So, one more question. Like in the beginning, you mentioned some Sanskrit word, some 300 kanta something.
Kakshas, actually, it's a temperature terminology.
Okay.
But kakshayas, actually it's kakshayas, but even I was not able to decode because the word kakshayas comes up with what kind of furnace that you are trying to use.
Okay.
So the furnace is something called as Kurma Vyasatika. So it is like a turtle shaped furnace which is being built. But I was able to decode only up to this. Beyond this, there are more to decode on this, which I was not able to do. So the problem is open. That's why I try to speak about those problems. See,
Okay.
it is completely open. We easily, you can go check. Robert Brill had come down to India to study about the. He started from the Alexander's this one, that is the Lycurgus cup, and he had come down to India to check the Romans Pudoke Indo-European trade. So when they were able to do so much, why not us? Is my question.
Yes, sir. So it is open for us.
Sir?
It is open for us then.
Yeah, it is open. It is open for anybody. See, it is a traditional knowledge. You cannot patent it, right?
Yeah. Yes. Okay, sir. Thank you.
Thank you.
Is there any question?
Sir, if we prepare the same composition glass with using the furnace and by using the microwave oven, the properties and the optical properties will be remain same or different, sir?
Ma'am, again, first, if I have to tell you, the properties will tend to vary in a very, very, very small quantity. Okay. That is because, the mechanism is completely different here. And you cannot try to use the same glass matrix. Say, for example, the precursor that you're trying to use here is going to be sodium hydrogen phosphate. Whereas when you're trying to synthesis the melt quench technique, you will try to use orthophosphate, as well as you're trying to use the sodium carbonate together. So precursors are slightly varied, and thereby the one what you try to see is also slightly variable. You don't see much variation in the properties, is what I'm trying to say. The trend might be the same, but the values might vary. say for example, if it is 3.2, it might be 3.5. Band gap might increase by 0.3 or 0.4 electron volts is what I assume, because that is what it happens.
Thank you, sir.
Yes, ma'am.
Any more questions? Tejas, you want to ask anything?
No, ma'am. Right now, I don't have any questions, ma'am.
Okay. Okay. I think no more questions. All are clear about your presentation, sir.
Thank you, ma'am. Thank you. Hope
Pratiksha,
hope I have given a very precise way of
yes,
information with respect to glass science, and it has hope I have delivered the purpose of your Creactive.
yeah, really, it's a very intense talk, actually, very depth and clear, sir. We
Thank you.
had so many diversions in this talk, and means up to a present trend, what the glass is changing the things, how it is changing. You included quantum computation also. So
Yeah.
it's a very intense application at present.
Yes,
So
ma'am.
it's a huge information, sir.
Okay.
Pratiksha,
Yes, ma'am.
out of
On
time.
behalf of our creative team and everyone present here, it's a privilege to propose this vote of thanks. We extend our gratitude to Dr. Abram Jaser for delivering an insightful and meaningful session on a castle of glass. Thank you, sir, for taking us on a remarkable journey through the world of glass science, from its thermodynamic behavior and networking architecture to the mechanism of bioactivity and advanced optical applications. Your explanation of how atomic modifications influence everything from bioglass tissue engineering to light control and many other topics was truly inspiring to us, sir. We are deeply grateful for your time, expertise, and the thought provoking perspective you shared with us today. Thank you so much, sir.
Thank you. Thank you once again. And I wish everyone all the best. And I would like to say that I'm always open for discussions on glass science. Anytime you can contact me, I'm available. Thank you very much for your patience